Okay, I think we are live on YouTube. So it's been a while since we've done this, so hopefully we don't have any hiccups here as we get going. I think I've got everything dialed in, and I think I'm seeing myself up on the stream, so it looks like we should be good. And unless I hear otherwise, we're going to start moving forward with this. So what are we doing today? We're talking about a couple scenarios that can come up inside of Dynamic Mill that can lead to some unfavorable cutting conditions, aka your cutter might break. So these things can come up. Again, there's two specific scenarios I want to talk about today, and it will, for the most part, catch the newer users off guard. So Dynamic, as we know, it's a tool engagement controlled tool path. So when you say to it, I want to cut a 10% step over on this tool path, it's going to maintain that 10% step over throughout the entire tool path, and it won't exceed that value. So when you've got that number dialed in as to the percentage that you want to cut, and you get your speeds and feeds dialed in with that value, you expect that you push go and it's going to be gravy all day long. However, these two situations can come up, and that otherwise perfect tool path can all of a sudden go sideways, and something might break, and you're not going to know why. So that's what we're going to talk about today. But yeah, I guess another thing we should bring up, why are we doing this live versus the usual videos that I usually do on this channel? So back when all this stuff started back in March of last year, of course I'm talking about COVID, we did a couple live streams, and we got some feedback on the live streams from people who normally watch the channel. And the overall, feeling was that people wanted to do more videos with the odd live stream thrown in. So we haven't done very many live streams. We try to focus more on videos. So we haven't done one of these in a while. And we also did the big event back in February. I can't believe that's already 2 months ago. And that was a big live event, and we posted the recordings from that event as well. So we've already got a lot of long videos on the channel, and so we don't want to do too many of these. I know it can be kind of boring to watch something that's an hour long of Mastercam talk. So yeah, so today we're doing this live to mix it up a little bit because we haven't done one of these in a while. And hey, I don't know, why not? Let's try it out. Okay, so what I got up here on screen, I'm pretty sure you should be able to see my Mastercam screen, those that are here. And we're going to be looking at Dynamic Mill again. And I've got two blocks drawn up here, 6x6. I'm going to tack one from the outside and one from the inside. Now I've got toolpaths pre-created here. I've already made them ahead of time, and the hope being that that cuts down on the length of this stream. I didn't want to go through creating all these toolpaths and have everyone watch me click buttons and enter in variables. But just know, for the most part, all these toolpaths are going to be doing the cutting with the same tool. I've used a 3/4 inch end mill. Speeds and feeds are all set the same for the tool throughout everything. So I think I've got 100 inches per minute as a feed rate, and 5,000 RPM or something like that, just so we can compare throughout different scenarios and see differences in cycle times and stuff like that. Okay, so the two scenarios that can come up that can break your cutter, what are they and why do they occur? So before we get into that, let's maybe have a look at how Dynamic Mill works. That'll give us a better understanding as to how these scenarios can come up. Okay, so first toolpath here, I've got, we're attacking this 6x6 block, and we're doing it from the outside. So first thing that might come up is, why are you cutting this shape with an end mill? Okay, so yeah, a shape like this, probably better to do a facing mill and zigzag across it, probably much more efficient. But I'm doing this to generate this cutting scenario that I'm trying to lead into. So there's a method behind the madness here, and there's a reason why I'm doing this. Okay, so with the outside, I'll hop into a back plot here, and we can see it's attacking the material from the outside and working its way in. Looks pretty straightforward, nothing really special at first glance. Now, taking that exact same toolpath and exactly the same shape geometry, the only difference here is I've switched the strategy to from inside instead of from outside. And the result here is a completely different toolpath. Obviously, we're cutting a different shaped part, but now we're starting at the middle of the part and working our way out and then picking away at the corners afterwards. Okay, so what does that tell us about how Dynamic Mill works? It might not be so obvious here at first, but what's happening is the toolpath is actually trying to stay in the cut as much as possible. So in this from outside, you're seeing absolutely zero retracts. It's always in material and it's always cutting, which is what we want. That's what makes an optimal toolpath. It makes it more efficient if it never has to reposition for a cut. Any reposition is going to be a retract, a reposition, which takes time to move when you're not cutting. So Dynamic Mill is doing exactly what we want it to do in a roughing strategy. Okay, same thing with the from inside. It's not obvious, but notice where it started this toolpath, right in the very middle of the square, which I guess seems kind of obvious to start there. Where else would you start in a square? It will come more obvious when we do some different shaped parts here, but the thing to notice here is it's starting at the middle and it's spiraling out. And what it's doing on this from inside strategy is it's placing its entry at the location where it can make the largest spiral before it starts picking away into the corners. Okay, so basically what we're trying to get at here is Dynamic Mill. Not only is it controlling the engagement of the tool in the cut, which is ideal for not overloading your cutter, but then it's also always trying to stay in the cut as much as possible, which leads to a more efficient tool path. Okay, so what happens if we throw something to avoid in the middle of this block? So here I've got a little 1-inch pin thrown kind of in the middle here, and we can see how the from outside tool path is adapting to it. Okay, so it's basically the same tool path for the most part, except it's dealing with this pin now just in the middle section here. So let's hop through a back plot. Encounters the pin. So even though it's encountered the pin, it's not changed its strategy. It's still trying to stay in the cut as much as possible with as few retracts. So it's not going to try and attack this from one side and nibble away. It's trying to stay in the cut as much as possible. Same thing with the from inside. Notice the entry location now of the tool path. It's shifted over to the bottom right-hand corner. Now, why is that? Again, it's tried to enter at a location where it can make the largest spiral out before it starts to nibble away at the corners. Okay, so again, it's trying to stay in the cut as much as possible. So now that we have an idea of how Dynamic's trying to address the material, I guess maybe before we move on too far, let's compare that to some other tool paths. Okay, so let's look at this is in basically the same kind of tool path, but instead of dynamic, let's look at an area mill tool path on the outside. So if we attack this whole piece of material, let's take away the boss. How does area mill differ from dynamic? So area mill, it's not a engagement angle controlled tool path. So this is more of just an offset. You're seeing a few retracts over here. Again, so as soon as we get retracts, we know our tool path is not as efficient as it could be. And no engagement angle control, so we're going to have spikes in our tool load, which if you're trying to push a tool to its max, not ideal. And then with area mill, again, if we threw the boss in, even more retracts now. And basically what this is doing is it's taking the shape that it's trying to avoid, and it's offsetting that pattern out to the shape that it's trying to cut. So this is good for a finishing tool path. That leaves a nice pattern on your machined floor. But if your goal is to remove material as fast as possible, area mill is not a great choice. If we're to compare this, so area mill, again, our speeds and feeds are all the same here. This is about 6 minutes, 47 seconds compared to the same tool path, relatively the same step over. This guy here in dynamic is 5 minutes 30. So just with the different strategy, you can see you're saving, 2-3 minutes of cycle time, which in the machining world is a big deal. Okay, so this is what we want. We want the behavior of dynamic mill. This is ideal. Let's take it one step further. Let's look at the pocketing. So go way old school and look at the pocketing tool path. So with this guy for pocketing, I've had to change the strategy over to facing, increase some overlap. We're still doing, a 10% step over. And the problem with this tool path is, you can see it right off the bat here, is a straight dive into material. So that's, if you're running at 100 inches per minute, 1.5 inches deep, it's probably not going to go so well. Same with those little transitions in there. So pocketing is not a tool angle controlled toolpath, and I think the biggest problem, as you'll see with this guy, is right there. If we were feeding at 100 inches per minute, cutting 1.5 inches deep, and we did something like this with our tool, that's an instant break. Okay, so again, back to Dynamic Mill. It's the better option. It roughs the part better. It's the toolpath we want to use 99.9% of the time when we're roughing parts out. All right, so we're all on the same page. We want to use Dynamic. We know the properties of Dynamic. We know what it's doing. Let's get into the problems that can come up. So let's take these parts and we now make them, instead of 6 by 6, I'm making them 6 by 12. So in our 6 by 12, here's the tool path. You know, same thing as before, exactly the same tool path, exactly the same settings. The only difference is the shape of the part we're trying to cut. When we backplot through this guy, again, everything is behaving like it should. It's trying to engage the material as much as possible, staying in the cut and not repositioning. It's controlling that cutter angle that's engaged in the cut. The problem here with this shape of part comes when we get close to the middle. So right in here, what you're seeing is this little sliver that's left behind. So what can happen here? So let's say this pen is the material. That's that sliver of material right in the middle, and this is my cutter. When I come down this side of the material, especially if you're doing a very deep cut, the cutting force applied to this material, if this material's got some ductility to it, it can deflect away from the tool. Okay, so that's not a big deal until you come back around the other side, and all of a sudden this piece that's tipped over that you would have engaged 10% of your cutter into is now engaging 30, 40, 50% of material because it's deflected over. And that unexpected load on your cutter leads, obviously, to bad things happening. So when you're pushing a tool at its maximum, you know, right in the boundary of, you know, breaking versus not breaking, and that's relative to that 10% step over. If you're now, getting into a cut that's 20% step over, things are going to go bad. Things are going to break. So this is the problem that can come up with Dynamic Mill. And it specifically happens when your part is exceptionally longer or taller than it is longer or taller. So if they're out of proportion by a lot, you're going to have this situation. This situation can come up. Not always, but it can come up. So if we were to add a boss to this, put that same boss in there right in the middle of the part, this scenario here in this situation is, again, it's going to get even worse. So now we're almost, creating two slivers here. Okay, so that's the problem that can happen with the toolpath that's cutting from the outside in. What about a scenario that can happen on the inside and working its way out? So on the inside out, we'll hop right into let's hop into the non-boss one. Okay, so let's just turn that boss off. So we're just doing inside out 6 by 12. Notice the entry location here. It's not in the middle of the part, but it's still in a position where it's made the spiral the biggest that it can inside of the shape it's trying to cut. So it's still doing that, staying in the cut as long as possible before nibbling away at corners. But it's also shifted this entrance over so that it's getting more of this type motion in the tool path than the corner type motion. Okay, so this path here, everything is fine, everything's great, no complaints. The problem that can come up with the from inside strategy, let's add that boss back in, is right here. So we're into our parts, we're cutting away, everything's great, grand, groovy, another G word there we go. Until we get up into this section right here. What can happen here? Why is this a problem? Okay, so as I mentioned, we've got a 3/4 inch tool. We programmed it at 100 inches per minute. Okay, so that 100 inches per minute, when we're doing a straight line, the cutter is getting a consistent chip load. When we start to do arcs, the chip load actually changes. Let me bring this page over here for a second. And I did a video about this a while back, and Haas also did a video about this a while back. So let me just bring this over. So those might have seen this. If not, please go watch this video. It's a really good video. Mr. Terryberry here is talking about cutting a hole that's 550 in diameter with a tool that's very close to that feature's size. So he's got a 550 hole, cutting it with a 1/2 inch end mill. So the point being, this video, they go through, they talk about it. What happens is we're driving the center of the tool path, the center of the cutter in our tool path. So even though we're cutting out here on the edge, we're programming the middle. So when our in this example here, they're talking about 30 inches per minute. So when you cut out 30 inches per minute out here, the programmed tool path in here that travels at 30 inches per minute in here, your tool at the periphery is traveling much, much faster. Kind of the same thing that happens with your lathe when you're doing a G96 surface feed call. The RPM at 1 inch is much different than the RPM at 100 thou. Okay, so this is the same thing that's happening. So you go ahead, watch this video. They even go through and near the end, they talk about a formula where you can figure out the feature that you're cutting versus the tool that you're cutting and the feed rate that you want, and then what the feed rate actually should be. Okay, and that's that formula. We'll come back to that in a second. And they did talk about in this video as well that you can do this in Mastercam, to which, let me bring over another screen here real quick. I did a follow-up video on talking about how you do this in Mastercam, how you can fix that feed rate automatically within some tool paths. Specifically, that tool path is the Contour 2D, not anything like this inside of Dynamic Mill. So let's talk about that for a minute. If I zoom in on this tool path, zoom way in. I know in the tool path itself, I've told it that I'm allowing a minimum toolpath radius of 10%, which is 75 thou. So basically what I've said to this toolpath is you can't make any arcs smaller than 75 thou radius. And so obviously it's fit through here, fine. And it with that minimum value, it still fits through. If I do an analyze toolpath on some of these arcs, let me just grab a random one here, say right there. You can see, well, the arrow's in the way, but basically I'm looking at about 177 there. There's the rad. 155, 150. So we'll say 150 is the smallest radius that this toolpath actually makes. Okay. So using that formula they talked about in that video, let me just scroll off to the side over here for a minute. I guess you don't really need to draw this stuff. I can just explain this with math. So basically, okay, so if we have a 3/4 inch cutter and we're making a 150, we're programming the center of that cutter and we're making a circle that has a radius of 150. Let me bring up my calculator here. So to figure out the diameter of the hole that tool is actually cutting, we take the diameter of our cutter, 3/4, and we add that radius of the tool path to it twice. Plus 150, plus 150. So in that section of tool path right there, we're cutting a circle, basically, that is a diameter of 1 inch 50 thou. Now, if we get back to, let me just bring back Mr. Terryberry here for a minute. Get back to his formula. Notice they say here, so to calculate the corrected feed for this feature, we would take our feed rate, multiplied by basically our hole diameter minus the tool diameter, and all that's divided by our hole diameter. So our feed rate in all of these tool paths is 100 inches per minute. Okay, and we're going to multiply that by the hole diameter, which I said was 1 inch 50, minus our tool diameter, which we know is 3/4. And we'll take all that and divide it by our hole diameter, which was 1 inch 50. So I'm getting a compensated feed rate of about 28 inches per minute. So according to that, to maintain this chip load that I intended to program with 100 inches per minute, in this section of the toolpath in here, I should only be feeding at 30 inches per minute. I'm feeding at 100 inches per minute. Okay, so as you can imagine, if our cutter at 100 inches per minute is right on the border of breaking And the equivalent to 100 inches per minute inside this section of the toolpath is 30 inches per minute, and we're feeding at 3 times that, we can have a problem. Okay, so how do we go about addressing that? So there's no override, there's no feed rate override inside Dynamic, so there's no switch that we can turn on to fix that, but we'll have to address it. Okay, so let's get back into this. So there's our 2 scenarios that can come up. Number 1, the sliver inside of a from outside toolpath, and number 2, small arcs allowing a tool to fit into a tight section that gets our feed rates higher than, or our chip load higher than we expected. I guess we could make the argument in this section as well. Maybe your machine tool can even accelerate fast enough to achieve 100 inches per minute on an arc that small. We'll leave that out of the argument for now. Let's just ignore that fact. We'll ignore your reality and insert my own. Okay. All right. So we talked about the 2 scenarios that can come up, why they come up. Let's talk about how we can fix them. Let's just move this down. We're into our fix section here. Well, let's turn that off. I'm giving away all the answers already. Okay, so let's look at from outside first. Let's get that toolpath up there. So there it is. So how do we not cut the sliver? So lots of things we can do here. Number 1, so we saw how Dynamic addresses material when we cut from the inside. So let's say with this problem shape, instead of cutting it from outside, we switch it and we cut it from the inside. Okay, so for that, we've had to draw a new boundary outside of the shape that we want to cut. So I'm using a 3/4 inch cutter here, and I believe I offset the distance here, analyze distance from here to here. That's 1/2 inch in radius, so that's more than the 3/8 radius of the cutter. So I've expanded the shape I want to cut, used that as my cutting boundary, and this will, let me just move this guy over here. This now cuts that entire shape that we wanted. We are avoiding the sliver. The downfall is we need to get into the material with most likely a helix. Is that the best way to go about it? I don't know. It's not my first choice of getting into material if I have the option to plunge outside. I would much rather plunge outside and deal with this stuff than do this. But you could drill a hole here. You could drill a hole that's maybe 10 thou shy of your floor, and then you're only helixing into 10 thou of material, and that would definitely work. So that's possibility number 1. Switch the strategy to from inside, draw a bigger boundary, and cut it like that. What's another option, what we can do here? So we can just avoid cutting this section altogether. So what I've done here is I've drawn, just freehand, I drew a block that basically encompasses where the sliver would happen. I add that to my chaining geometry as an avoidance region. Up in here, it's in my avoidance region. So I'm avoiding the boss, and I'm avoiding this box that I've drawn in to avoid cutting the sliver. So do we avoid cutting that sliver? Hop into a backplot here. Oh, I made some changes there by accident. And yeah, so we avoid cutting that sliver, but now we need to come back afterwards and deal with this section of material, however we go about that. We could do a contour in there, clean that up, do a pocket, whatever it is. Maybe instead of the dynamic mill, it's cutting 1.5 inches deep. We attack this middle section here where we only go, maybe we do 3 step downs of 1/2 inch each time, and that avoids the sliver, or at least keeps that sliver strong enough that it can take the cutting forces and not break away or rip off and get into the cut. So that's another option as well. Other options, let me go for maybe the most obvious one, but I think before we get into more of these, another way you can look at fixing this toolpath is you just need to eliminate the disproportion between the width and the height. If you can get that squished down to being more of a square-ish shape, the closer you get to square, the less sliver there'll be here, and the less you need to worry about it altogether. So you don't need an exactly square part, but if your part is 20 inches long by 2 inches tall, if you can squish that 20 inches down somehow to maybe 6 inches long by 2, that will probably machine just fine. So we just need to look at different ways we can squish off that excess that's out of proportion in this toolpath. So ways we can do that. So here I've got a boundary drawn up right here, and we're machining this part of the part on its own. And then we attack this part over here the same way we did with the 6x6. So we're doing it in two separate tool paths. One, to get the tool path more squarish, and then the second tool path dealing with it as the square-ish part where we don't get that sliver scenario. So ways that we can eliminate that half. There's, you can go old school, grab a contour, hit this one edge, chain one thing. The problem with the contour is we have to calculate how much stock we need to leave. So if I'm chaining out here, how much past that do I want to machine? I had a -6 in there, so let's just go with that, -6. And if we did this, we still now need to come in and calculate multi-passes, which I think I've already made this toolpath before, so let me hop into that. I've got it down here. There it is. Okay, so the problem with contour, again, it works fine. Oops, my speeds and feeds aren't coming through here. There we go. Yeah, so you need to figure out how much you need to overcut it, and then you have to come in and calculate the number of passes you need and the step over for that. So the step over we already know. We already know it's the 75 thou that we wanted to maintain that 10% engagement. But we would need to take our 6 inches divided by 75 thou, and that's what gives us our step over there. So with contour, it's doing, just straight zips across, retract, reposition. So lots of retracts. There's no way around that. There's no way that we can't. Okay, I'm saying that wrong. There is a way we can get around not retracting. That would be by doing a zigzag cut. But my argument would be, again, if you're in a climb mill scenario and you've got this cutter right on the brink of breaking as is, you're not going to want to conventional cut that cutter at those same values. So bad things will happen there. Cutting forces in climb milling versus cutting forces in conventional, much different on the cutter, and conventional probably won't go so well either. Okay, but then again, that's just a way to attack that material to get it back to a more square-ish size so that the dynamic then works the way we like it to work. Other things you can do in here, so peel mill. Peel mill is a nice one. This is a toolpath that does not get used very often. It's a long forgotten because I think we all prefer to use dynamic in basically every scenario now instead of peel. But don't forget, peel's got two different strategies in here. It's got dynamic peel and the super old school peel. Here I'm using the super old school peel. And I've just got basically a line drawn in right here at the middle. This is the geometry I've changed for this peel. I basically gave it a width, and we can extend or shorten if we needed to as well. So what you're seeing with the peel is basically the same thing as contour. Okay, so you're going to see a cut or a retract or reposition, and then the next step over. The added benefit of this peel mill is all I had to do was draw a line. Okay, I didn't have to calculate how many step overs given how far past the line I wanted to calculate. I've also got the option here for micro lifts and repositions. Instead of retract, rapid, over and down, I can control it with micro lifts, so that's an added benefit. With this one as well, it's easy for me to change the width as well. I can extend or shorten if needed. So peel mill, another good idea to chop off that long side of the part in order to get dynamic mill to work better on the other half. We can also do, so this guy here is doing a dynamic mill. Again, I've created additional geometry to create a section that I can get dynamic mill to cut half of the shape. Problem with this section here, or this strategy, so this toolpath right here is nice, okay? Nice big long arcs, nice consistent engagement angle until we get to that right there. So that right there, we're getting into that small arcs, the scenario we're about to get into and talk about with the from inside strategy. And we don't need to be nibbling away at these corners. There's no need for a sharp corner if we're going to be machining all this stock away anyway. So what we could do here is, we could fill it this shape of the corner. We could limit the tool path here as well. We could say, I don't want to be getting down that sharp, so maybe 400. That'll keep it a little bit flatter, but even still, that's probably getting too sharp. It's too much work in the corners for a part like this. And then also we need to keep in mind, if we were to do a path like this, that's not exaggerated enough. That's probably still not exaggerated enough. Okay, so let's pretend our toolpath ended right there. We would need a way to give the next toolpath all of this missed material in here for the operation to see. And if we're talking about 2D dynamic, unfortunately, we can't give 2D dynamic a stock model. Okay, so if we're talking about using stock, we wanted to use this leftover over in here. We would have to depend on, rest material, one other operation, and then picking one. We unfortunately don't have the option to use a stock model with Dynamic Mill. However, in 2022, that's not a problem anymore. So no matter what license of mill you have in Mastercam 2022, you can use OptiRough. Okay, OptiRough is basically exactly the same thing as Mill 2D Dynamic, except it can work in the three-dimensional area. It takes solid models, and it can also use stock models. Okay, so I'm not going to get into that today, but just thought I'd mention that. Even though we can't use stock models in 2D Dynamic, everyone using Mastercam 2022 can use OptiRough instead. Okay, so that's how we can fix the sliver scenario on the from outside style toolpaths. How about from inside and dealing with, let's get this toolpath back up here, this scenario down in here. So basically where our feed rate is higher than what it should be. It's higher than what we intend, I guess is the better way to say it. So what I would do is something like this. So again, the argument here could be made, the 3/4 inch end mill can probably take, if we're talking 100 inches per minute here, a 3/4 inch end mill could take the extra load in here. It's probably not going to care. It might bark a little bit, but for the amount that the machine can, how close the machine can accelerate to get to 100 inches per minute, it probably won't. So it might get to 50, 60, and on a 3/4 inch tool, it's not going to hurt it. But if we take that down to the other extreme and we're talking a 1/8 inch end mill, and we're getting into a very, very small scenario where maybe 10 inches per minute was pushing that tool to the limit, and we're getting into arcs, very tiny arcs, where we're exceeding the recommended chip load by 10 times, yeah, you could easily break that 1 inch or 1/8 inch end mill quite easily. So how do we address that? All right, let's get into that. So what we're going to do here is just not cut it. Okay, so plain and simple, we're just not going to cut those areas of the tool path with our tool at the higher feed rate. So this, to be even more exact, maybe this is 300, 250, whatever it is. So, and with this, we're going to limit how small we can get with this tool path. So I don't want this to cut anything less than a 1/4 inch radius. You want it to be extra safe, call it 400, call it, maybe 60%, whatever it is. But I'm going to leave this at 1/4 inch, not 25 thou, sorry, 1/4 inch. 1/4 inch for now. Give this a second here to regenerate. And we're not going to get into this area now, so I'll make a second tool path that hits only those areas, and in this tool path, I'll force my feed rate down lower, down closer to what something safer is. So yeah, theoretically this will take longer in your cycle time, but if you're breaking cutters going at 100% feed rate the whole time, this obviously is faster than switching out end mills and explaining to your boss why you broke the 7th cutter in the exact same part on the tool, or they're in the part again. So how did we get this to cut the right section of the part? So in this source or original toolpath here, I said quarter inch. Quarter inch was my minimum toolpath radius. Okay, so quarter inch. So when I go into my 2D dynamic, again, we don't have access to stock model in 2D, so I can't make a stock model from the previous operation unless I wanted to use OptiRough. So in here, you could use the previous toolpath, but using a roughing tool diameter is way quicker as far as the calculation time of this resulting stock toolpath will be. And I find it to be much more accurate as well. You've got more control over how much you're cutting. So basically, with a quarter inch radius, I took the 3/4 inch cutter, added the radius to it twice, gives me a roughing tool diameter of 1 1/4 inches. And this one, then I've set that minimum toolpath radius back down to fit so that it does fit up into here. Okay. So this will make tool motion only in the uncut sections at the reduced feed rate. Okay, so we get these two tool paths, and we can run through them both. So here is the reduced arc toolpath, or reduced min radius. And this is our second toolpath that now comes in and just finally nibbles away at those corners at the reduced feed rate. Okay, so I think we covered quite a bit there. I got that done quite quick too. I was hoping to be well under an hour. And I think making these toolpaths up ahead of time helped keep things going. We got a comment here from Oleg. In Dynamic, you can create geometry for your entry method profile between wall and the round ball. Yeah, you've got lots of options in Dynamic for your entry chain. And then you can pick how that comes in over here as well. Yeah, so I didn't want to get too much into entry motion, but I guess, yeah, maybe the argument you're making is you could ramp down through these sections as well, or you could ramp over there in your sliver as well instead of doing a helix. Absolutely. But yeah, the things I wanted to focus on here today was, how you can first recognize when that sliver scenario is going to happen in your parts, how you can address it to avoid it, and also how you can avoid overfeeding your cutter in tight areas of your part. Okay, so I think that went well. Nothing broke anyways. So other than that, so I think we're going to wrap it up. I just wanted to do a quick little demo today on Dynamic. This will be recorded. It will be posted up on YouTube here shortly. I'm also going to repost it over on the blog page, camInstructor.com. I will post links as well to those two videos I mentioned, the one from Haas about talking about the formulas and the cutter versus feature diameter. And I'll leave a link to our video as well, what talks about how you can compensate for stuff like that in Mastercam. Other things I didn't bring up this high feed guy. This is something that you could use in scenarios like this down here. Yeah, it can kind of work, but I don't think you're going to really get the optimal performance that you're after out of it. So I don't know. I'm just left that one off the table. If you want to experiment with it, let me know your results. But yeah, there's always that option as well. Okay, so I think I'm going to wrap it up. That's 40 minutes of me rambling on about Dynamic Mill. I think it's more than enough. And I guess, yeah, we'll say thanks everyone for joining in today. And stick around. We'll be doing another one of these sometime soon. Maybe before the next year goes by, we'll do another one of these. All right, everybody, take care.